All right, so we are starting this part on ecology, and this video is going to focus on populations. Ecology can be studied many different ways, from individual behaviors to groups of one species to all the living things to the living and non-living things like um, all the abiotic factors, the non-living things that come in as well. So this one's focusing more on the population, all of the individuals of one species in a given area. So as we focus on this, a lot of things that ecologists do is count up what's there, what's around. So as they're looking at that, you have numbers, you have time, things change over time, and that's how we are looking at our populations. So you're going to see a lot of things like this, and you have to be able to read the graph and interpret why things are what they are. So you might have another one of a different species, but then eventually we get into mixing um, species together in the same graph, and that's not what this video is. That'll get into the community and the ecosystem things, where we look at the interactions and how one thing affects another thing. But for now, we're just looking at one population, one species at a time. So we often see different types of growth curves. We have exponential and we have logistic. So a lot of times logistic is called an S curve and exponential is called a J curve. With these growth models, we're going to first look at exponential growth. So ultimately, if a population is changing in size, you figure that out by births minus deaths. If more are being born than are dying, your population is going to increase. If more are dying than is being born, your population is going to decrease. To find the rate of increase, we look at these things and we divide it by time because that's what rates do. So if the rate is zero, we have zero population growth. However many are being born, we also have that same number dying. So the R would be zero in that case. Now, we also can have maximum population growth if nobody's dying. If everyone is born and everyone continues to produce offspring, it gets steeper and steeper and steeper. The more individuals you put there, the more possibilities for offspring. So is exponential growth real? Does that really happen like within a certain environment, but it won't go on forever? I mean, obviously, right? If E. coli bacteria reproduced at top speed and started with just one bacterium within 36 hours, that's it. There'd be enough bacteria to cover the earth with a 1 foot layer of bacteria. Now, obviously, we aren't wading through bacteria, so exponential growth has limits. And when you start looking at AP stuff, you have this on your formula page, where we start looking at all of this algebraic equations here. And again, we were just talking about population growth and rate involving time, and population involving births and deaths, and exponential growth. As the number increases, the rate will also increase here. So when you see this, we're thinking about the rate, okay? Now we're going to get into this thing with logistic growth. So if we're looking at the growth rate here, we are using the population size, which is represented with an N, and we're introducing this K, and K stands for carrying capacity. So if we look at this, the carrying capacity is the maximum stable population size that a particular environment can support. So now we're tying all this math in here. So as we go up, this is the maximum growth rate, right? As you increase the number, you're going to increase the rate. But again, as we approach our carrying capacity, we limit the growth rate. So let's take a look at these numbers here once. So the carrying capacity here is 1,500 individuals in an area. The closer you get to 1,500, the smaller the rate will become because the multiplier here gets smaller and smaller. Now, once the population N hits the carrying capacity, If the number of individuals actually in a population is the same as the carrying capacity, we now have a zero on top of this. So if you multiply by a zero here, your growth rate is zero, and that causes it to level off, where it's not going up and it's not going down, it's steady right at the carrying capacity. And that's how we get our S-shaped curve. So now, when this rate hits zero, does it mean that that population is not healthy? That's not necessarily what it means. It's just it's at the maximum capacity for that environment. And how does that relate to birth and death? Well, if the population isn't going up or down, it doesn't mean that there aren't new organisms being born. It just means for every organism that's being born, we're also having some die. It's stable. So, all this talk about carrying capacity, and again, when you hear carrying capacity, we're thinking K. Okay, when we're thinking about growth rate, we're thinking R. So, what determines the carrying capacity? Limiting factors ultimately determine it because there are going to be factors in an environment that are going to limit the size of the population. There's going to be something that's going to limit the ability of bacteria to reproduce and grow. Now, what are those limiting factors? We can tie in density dependent factors. So, as the population increases, these factors have a greater effect. So, when the population is really small, there isn't very much competition for food or water or shelter. But as you get more and more individuals in that population, the competition becomes greater and greater and greater. And all of these things have a greater effect. There's going to be more toxic waste accumulated in a bacterial colony if the population is really high compared to if it's really small. They're going to limit their own growth because of what they produce is going to ultimately kill them. So diseases are going to transmit from one individual to the next easier if the population is more crowded. If you're real spread apart, the disease isn't going to spread as easily. There can be more predation if there's more prey. All of these things are going to increase the greater the competition gets, the more individuals in an area. Now, there are some things that have no effect on the population, doesn't affect these at all, that can also limit carrying capacity. If you have natural disasters, I mean, it doesn't matter how crowded organisms are, they're going to get wiped out one way or another. So when we start looking at this, you have this part of the growth curve and you have this part of the growth curve. So this is a really common type of question. In one paragraph, explain the biological factors that determine the shape of the growth pattern in period 1 and period 2. So during period 1, we have a lot of growth here and it is starting to slow down towards the end, but this is a pretty steady rate of increase. So there's definitely going to be more being born than are dying because the population is increasing. Now, they haven't filled up that environment. We aren't having these huge amounts of limiting factors kicking in now. In period 2, we're going to have the same, we're going to level off here where we hit the carrying capacity and the number of deaths is going to equal the number of births. So, one thing that we can transition on, and again, we're going to keep this in mind, this R and this K, as we move a little bit further here. Now, we have R selection and K selection about different types of individuals, but let's look at some more graphs and see if you can make some sense out of this stuff. This type 1 group, survivorship, here are all the survivors. There's a lot surviving at a young age, a lot surviving, a lot surviving, and then as you hit towards upper age limits here, we have a lot dying all at once. You also have another group of species where they have a lot of offspring, but they die really quickly here. But then if you get past a certain age, your chance of survival is really good. So we have this type 1 and type 3. Again, it's the ability to read a graph, right? Now, what kind of species are type 1 species? Ones that we have a long lifespan. We take care of our young, even though they might be helpless. Um, type 3 species, they have a huge amount of offspring, but they don't take any good care of them whatsoever. So a lot of them die right away, but they've had so many that the population can still like handle it. These type 2, if we're looking at this maximum lifespan, the number of survivors is pretty steady, so it's not an advantage for a squirrel. I mean, they're getting killed off at the same rate no matter how old they are, is basically what this is saying. So, again, when we look at these survivorship curves, if we have this semal parity, we have big bang reproduction where we create a huge number of offspring and then typically the parents die. They make the babies and then they're done. They have one big shot at it. Heteroparity means that there's repeated reproduction. They're going to have just a few offspring. They're going to take care of them as they move on. They're going to have some more babies and they're going to take care of them and they're going to move on. And this is repeated reproduction. Examples like chimps, taking good care of them. They're what we would consider a K-selected species, which we're going to get to in just a second. Something like salmon, one big generation, laying a tremendous amount of eggs, and then they die. So they're not taking care of their eggs. They are just booming their birth, one big reproduction, and then it's over. So now, as we look at these growth models, this is a lot of what ecologists do is they model the growth. So we can have mathematical models, which is what we're looking at here, instead of just like procedural models. We have R selected and K selected. R selected species have a huge, again, what was the R for? The rate of increase. So when we say this R selected species, we're talking about this huge rate of increase or the potential for a huge rate of increase. We're going to have big bang birth. Typically, there's going to be high offspring mortality. They're going to die a lot. However, sometimes these R selected species can have a huge exponential growth rate at first because there aren't a lot of mortality. If you're invasive, if you're a new organism in an area, they might not have any natural predators, so their death rate is actually really low and they have huge exponential growth. Now, we also, these types of species also thrive in situations where they're operating well below the total carrying capacity. So you get to see this big exponential growth, this big R rate of growth. One example of that would be the zebra mussels. They're native to lakes in Russia, but they've come over in ships to the Great Lakes. So this is just a phenomenal thing here. Amazing, right? It's really harmful, but they can begin reproducing within 6 to 7 weeks. They can reproduce 1 million eggs in a year, 30 to 40,000 at a time, and can live 4 to 5 years. If there's nothing naturally killing them off, that is going to create a humongous exponential growth curve. Again, we're calling this big exponential growth R selected species. We can also have K selected species. They take good care of their offspring. They operate close to K, carrying capacity. So they are favored when when it's real close to carrying capacity, and they typically have more stable populations. Their fluctuation in their populations is much less. So when we start talking about exponential growth, we said that's not really real, right? Because it can't go on forever. Something has to ultimately limit its growth. But is this logistic growth real? Do they perfectly level out where the carrying capacity is met, the same number are born, same number die? Is that really real? Well, let's look at some things. Both of these species tend to overshoot the carrying capacity a little bit. Again, this is boom and bust, right? So our selected species make a ton of babies and then they all die, and then a ton of babies and they all die, and they overshoot a lot. They drop way beyond what they can handle, and then they crash. But they can rebound really fast because they can make so many offspring at a time. Because they don't take care of them, a lot of them die off, or they can't handle what the environment um, wipes them out because they just can't handle that many babies if they all survive. But then K-selected still overshoot as well, and all of these overshooting the carrying capacity it's going to lead to competition. Right now, there are going to be things that die, and there's going to be things that live. Here, the same thing. A lot of them die, but some of them are going to make it and pass on their genes. So, overshooting carrying capacity leads to competition for those limited resources. Ultimately, that's survival of the fittest, and that's evolution through natural selection. Those that are best adapted will pass on their genes to the next generation. But again, our K selected species follow more of an S curve, hit more of a plateau near the carrying capacity, and our R selected species have these boom and bust cycles. So let's think about one example, a moose. Are they R or are they K? Now, if you just look at this graph, it almost looks like this boom and bust kind of thing because you have steep lines and everything. But do they care for their offspring? Are they focused on repeated breedings? They are a K selected species. However, things can happen at certain points in time that have traumatic effects on their population and kind of crash things. So ultimately, let's look at this. Number one, what would be about the carrying capacity of moose on Isle Royale? They're going to overshoot, but at the same time, it can only handle so many moose. Now, question two says that these real populations don't follow perfect logistic growth models, where once the carrying capacity is reached, it just balances out perfect. Death rate and population is perfectly stable. But at the same time, there are limiting factors. What are abiotic, which are non living, or biotic living factors that could be responsible for the collapses or decreases in the moose population? What's going to limit the availability of or ability of the moose to their population? Now, when we start thinking about those density dependent factors that limit the population growth, how would that affect the evolution of the moose population? So think about something that you mentioned in here. If someone is better adapted to these factors that are going to limit them, how could the overall species change slowly over time? Are they going to sprout another set of legs and run faster? Probably not. But if they have a hard winter, those with the thicker fur might be able to live longer, and you might see a little shift in the population of the moose towards thicker fur. So ultimately, when we look at population ecology, we're looking at graphs. Birth minus death gives us our population. When we look at the rate of change in the population, we're looking at change in population over time. So when we have rate, it's over time. Carrying capacity is represented with a K, and the carrying capacity limits the rate. What determines the carrying capacity? Both abiotic and biotic factors. You should be able to come up with a list of those. We also talked about reproductive strategies, R versus K species, those that reproduce more exponentially versus those that stabilize close to the carrying capacity based off of how they care for their offspring and the number of offspring they typically have. Again, let's make some evolutionary implications about this. What is it that gives them the greatest advantage to pass genes on to the next generation? And also, let's always tie this back into invasive species. This is a really important thing, both globally and locally. They're going to be more R selected, where they can, we have very few deaths and a big boom burst, so then they can really take over an area. In addition, K species are oftentimes most damaged by a disturbance because they do have small numbers of births. They can't recolonize quickly the way our species do. But these are the high points when we start talking about population ecology.